how to solve the boundary layer problem. Now today we will start with what is called the approximate method for solving. And the reason why I'm doing this is, again, more than the exact methods to solve equations need not be fluid mechanics. It could be in any field. And so these approximate methods are is what we'll discuss. And to start with these approximate methods, we first need to define different type of boundary layer thickness. Did you see some of this in your undergraduate course? The different type of boundary layer thickness. I don't know, at least I was not able to cover in APL 106 this topic at all. I don't know what about 107 or 108, whatever course you were doing. 107.
So we read about boundary layer on a flat surface only.
Okay, let's see. So let's define some different type of boundary layer thickness. And the first boundary layer thickness is the normal boundary layer thickness, which is basically what we refer to as delta. And this is the boundary layer thickness is the distance from the wall where small u becomes equal to capital U. Okay. So we have this flow. This is boundary layer. And this flow at the boundary, capital U of X is the external flow. So the distance from the wall where U of X is equal to, where U, which could be X or Y both, where U is equal to capital U. That is what we call as the boundary layer. But now there's a bit of a problem, because theoretically, as we have seen, small u is equal to capital U at y is equal to infinity. So instead of imposing small u is equal to capital U, we say small u is equal to alpha times capital U, where alpha is a scalar less than but close to 1. And what we say is, and we represent the boundary layer thickness as delta alpha. And for example, delta 0.99 distance from the wall where small u is equal to 0.99 times capital U.
Excuse me, sir, are you writing something because the screen is frozen from, for example?
अच्छा अभी for example अब आ गया कि नहीं आया?
No, sir. Now it is
अभी
visible.
okay. So anyway, I'll wait for a second. So what I was saying was, for example, if you say delta 0.99, alpha you say is 0.99, then this will be the distance where from the wall where small u is equal to 0.99 times capital U. Of course, since you know the boundary layer is thin, this delta will not be a very big quantity, but one thing we have to keep in mind is delta will be a function of x. This is the x direction. Delta always is a function of x. And normally we take alpha as 0.99, but if you want to be more precise or less precise, you may take it as 0.95. But if we don't write anything, then this is supposed to be about 0.99. A very loose type of thing, but nothing very sacrosanct. Okay. Next, we define a more rigorous thickness, which is called displacement thickness. And let me first define this and then give you the motivation. Displacement thickness is represented as delta star, or in some books you will see it as delta 1. And what the definition? Delta star is equal to integral from 0 to delta 1 minus small u upon capital U dy. So let's try to understand what this is, and let me draw a cartoon. If this is the boundary layer, I look at any distance x from the plate. Here, the velocity distribution x component is u of y, and at this point, this is equal to capital U because you have gone up to delta. This height is delta. So now let us see what is the motivation of defining a thickness like this. In the boundary layer, small u is equal to u of y at a given x. So the actual mass flow rate, and this is obviously, we're talking of a 2D case, so this is per unit width. What will be the mass flow in this cross section from 0 to delta? Can anyone tell me what sort of an integral will this be? What is the actual mass flow?
So integral uy dy.
Integral rho times u of dy with limits going from 0 to delta. Is that fine?
Yes, sir.
Does
Yes,
everybody
sir.
understand? Okay. Now, if there was no boundary layer, then m dot, and I call it as ideal flow because there is no boundary layer. What would be the mass flow rate per unit width if there was no boundary layer? What integral would it be?
So u infinity into delta.
Rho times capital U dy from 0 to delta, and because u is capital U is only a function of x, so you're right that this becomes equal to rho times capital U times delta. Okay, is this clear to everyone?
Yes, sir.
Others also, I assume those who are quiet have understood. So now what one can see is, one can think of the boundary layer, that boundary layer is causing a mass flow deficit. Actual mass flow, if there was no boundary layer, would have been rho capital U dy. And in this figure, how would I show this rho capital U delta? What will this be in this figure?
A rectangle.
It will be a rectangle. If I complete this, so maybe let me change my color. If I, the ideal mass flow rate here would have been, you're right, it is the rectangle. Let me now show this with the red color. If, sorry, if I don't take this. This red colored rectangle, this is rho u delta. Whereas the area this area is rho u dy integral from 0 to delta. Is this clear? So once you understand this, then you can think that boundary layer is actually causing a mass flow deficit. And one way of interpreting the deficit is that we lift the body surface up by a quantity called delta star. That means whatever is this deficit, instead of the body being at y is equal to 0, if the body is at y is equal to delta star, and now if the mass flow rate with that ideal flow being from delta star to delta is the same as the actual flow, then that is what we are doing by saying that we have lifted the body by delta star. So let me just write this and then I will give you some time to think about it. So the deficit, which is equal to rho u times delta star, this is what one can think of the as the deficit, and this is equal to rho u delta minus rho times integral from 0 to delta small u dy. And from here, when I now write this, delta star will be equal to, I can just think about it, 1 minus small u upon capital U dy. Things which do not depend on y, I can take them in and out, which do not depend on y, I can take them in and out of the integral. So that is what I have done here. And this is how we have defined the displacement thickness. Let me take a small pause and see if you have understood this. Is this clear?
Yes, sir.
Yes,
बाकी
sir.
लोगों को?
Yes, sir.
Okay. So this is why how the physical motivation of defining the displacement thickness. We also define a second thickness called momentum thickness. And the symbol we use is either theta or delta 2. And theta is defined as integral from 0 to delta small u upon capital U into 1 minus small u upon capital U dy. And let's see what the motivation for this is. Again, these thicknesses have been defined because they will help us they will come in some equation which we will derive later. But I'm starting with these thicknesses and giving you the physical feel for these thickness. Now here, let's see the actual mass flow in the boundary layer at location X is integral from 0 to delta rho u dy. We have already seen this. Now, if this actual mass flow had a velocity capital U of X, this is the mass flow. If it had the potential flow velocity, then the momentum flux of this flow would be capital U times integral from 0 to delta rho u dy. And this I can write it as integral from 0 to delta rho u capital U dy. Because capital U is not a function of y, I can pull it inside the integral. Okay. So this is, and the actual momentum flux, this is, if the actual mass flow had the velocity of ideal flow, that would be the momentum flux. And the actual momentum flux in the boundary layer, what the actual momentum flux? Integral from 0 to delta rho small u square dy. So once again, as before, we say that there is a momentum deficit due to the boundary layer, just a way of thinking. And this deficit, which is equal to rho, this leads to boundary layer thickness theta such that the deficit which we have, which is rho u square theta, this is equal to, the ideal case was rho u times capital U minus, the actual case was rho u square dy. And from here we define theta is equal to integral from 0 to delta small u upon capital U into 1 minus small u upon capital U dy. So this is the definition of momentum thickness. Okay, is this clear?
Sir, please scroll up a bit.
Actually, some of you may, I don't know if some of you are getting intrigued. Why did we take the actual flow and used its uh, ideal flow velocity to calculate the first flux? Somebody could have said you could have taken the ideal flow itself and multiplied by capital U.
Yes, sir.
Is that what you were asking? See, I could sort of guess that, because
Yes,
I
sir.
also had the same question. But in some sense, what we are trying to do is we are trying to maintain a mass balance. That mass balance tells us in the actual flow, the flow is actually rho small u dy. So we are fulfilling the mass balance and then saying if this flow had the ideal velocity. Maybe we can define a new thickness where the first term will be rho capital U square. That would be another thickness.
Yes.
So then one could define, and the first term would be capital U square, and what you would get is 1 minus small u square upon capital U square. So that also could have been done, but this is defined, and probably the motivation for that is you want the continuity equation to be satisfied when you use the momentum equation. If you recall, when we do integral flow analysis in the first course, the first guiding principle, at least which I teach, is mass balance has to be always satisfied.
Yes.
Yes.
So that is why we are defining it like this, but nobody prevents you from defining a second thickness, which is 1 minus small u square upon capital U square dy. And as you will see, the reason why it has been defined like this is basically because what the equation which will follow will need this theta. So that is why maybe it was done like this. Okay. So now let us talk of the approximate equation. But before that, let me tell you something which probably a bit of maths once more. I don't think we did this in the start, or did we do this rule in the start? Leibniz rule. Is any of you aware of this? Now, this rule is if you have d by dx of integral of a function which is a function of x and y. And the limits on this are what would you expect this to be if I want to take the d by dx inside the integral? How will I do it? And this, let me specify, let me tell you. So this will be, let's take the d by dx inside. So this will be integral from alpha of x to beta of x. And now because f is a function of both x and y, partial f by partial x dy. This is sort of fairly obvious. But now, because alpha and betas are not constant, I will get two more terms. The first term will be f of x comma beta d beta by dx. So I replace whatever is y by the upper limit of the integral and minus f of if alpha and betas are constants, then I will just get, I can take the derivative inside. But if alpha and betas are functions of x, then I have to use something like this. And this again is something which is very general. You may need it at other places also. So just, it's sort of very intuitive to feel what this rule is. But is this clear to everyone? And essentially what this is doing is it is taking care of the change in f with x, which has taken place over this range of delta y. Over this range from, yeah, over this range delta y, there is a change in f with respect to x. And that is accounted for by the last two terms. Have you seen this before or no?
Yes, sir, I have seen this, but I
Where?
mean, intuitively, I am not imagining it.
Intuitively नहीं हो रहा मैं अभी I don't have that. If you look at, it's given in many textbooks. Penton's book वगैरह में एक बड़ा clear इसका intuitive वो भी दिया हुआ है. So anyway, just take it as a mathematical rule and let's now. So we'll use this in our derivation. Also, we have defined these two quantities. So let us now look at the boundary layer equations. The boundary layer equations are and we have the continuity equation. Now what we do is we integrate these equations with respect to y with limit 0 to delta. That means integrals integration 0 to delta x. This whole equation dy. So we'll integrate both sides, whatever is the left hand side, and we integrate these equations. So now let's start with the continuity equation. The continuity equation is integral, we integrate this 0 to delta. I just inverted dv by dy minus du by dx. And the reason is I want to get the value of y. So now the first term here becomes basically, so integral dv by dy will become, when I integrate this with respect to y, this will become v partial v by partial y with limits from 0
Sir,
to
why
delta.
there is minus sign?
Oh, there is a du by dx, dv by dy. Sorry, there is a dv by dx is equal to minus. I should have, is equal. I forgot the equal to sign. So this is, let me, is equal to minus. I'm writing it in an equation form. So I'm equating, the left hand side becomes v with limit 0 to delta, and this will be equal to minus integral from 0 to delta du by dx dy. And the upper side becomes v at delta minus v at 0 is equal to minus integral from 0 to delta of x partial u by partial x dy. Okay. Now, if the plate is non-porous or the surface is non-porous, this implies v of 0 is equal to 0, else v of 0 is equal to v0, the velocity, normal velocity at the plate. If there is a hole in the plate, then this will come. Otherwise, we get v at delta will be given by minus integral 0 to delta of x du by dxt. Okay. Then we move to the first equation and we integrate both sides, integral 0 to delta dy. See, what do we mean by integrating an equation or integrating something from 0 to delta dy? That means we are, whatever is the y component, we are in some sense averaging all that. We are keeping only the functionality of x, and whatever there is in y, we are summing it all up. That is the meaning of integral with respect to y. So the first equation, which is u du by dx plus v du by dy, is equal to capital U du by dx plus nu d2u by dy square. So let's integrate this from 0 to delta, both sides with respect to y. So let's do it term by term. So this becomes equal to integral from 0 to delta u partial u by partial x dy plus integral from 0 to delta du by dy is equal to integral from 0 to delta now when I integrate d2u by dy square, this will become the first derivative with limits being at 0 and delta. Okay, is this fine? Next, let's now look at u du by dx. This I can write it as partial by partial x of u square. And v du by dy, this can be written as partial by partial y of v times u minus u times partial v by partial y. And this I can write it as d by dy of vu plus u times du by dx. And this will become d by dy of v times u plus half times d by dx of u square. So once I combine these two, integral 0 to delta u du by dx plus v du by dy. This becomes equal to integral 0 to delta partial by partial x of u square dy plus integral from 0 to delta d by dy of u times v dy. Okay. And this term I can write it as, now the second term, integral from 0 to delta d by dy of uv dy, this will become equal to uv with limits from 0 to delta, and this will be equal to u at y is equal to delta times v at y is equal to delta minus 0. Minus, it will be basically u at y is equal to 0 times v at y is equal to 0. And this will become equal to capital U, and v at y is equal to delta. We have already written this. V at y is equal to delta is equal to minus 0 to delta times. Because u at y is equal to 0 is always 0. V at y is equal to 0 may not be 0, but small u at y is equal to 0 will always be 0. So therefore, the left hand side becomes integral from 0 to delta d by dx of u square dy minus capital U integral from 0 to delta partial u by partial x dy. Okay. Now we have this. Now let's look at integral from 0 to delta partial u square by partial x dy. This will be equal to, using Leibniz rule, d by dx, I can pull it outside the integral of u square dy minus the value of u at delta, which is capital U square d delta by dx, and then there will be a plus term which will be 0. So basically, if I look at d by dx of 0 to delta u square dy in terms of Leibniz rule, this will be, I take the derivative inside, which is the left hand side, plus the value of u at y is equal to delta, which is capital U. So u square times d delta by dx, and then there will be plus 0, because the third term will be the value of u at 0, which is 0. So is this clear? And if we look at the second term, integral from 0 to delta, we need du by dx dy. This is what comes in the second term. This will be equal to d by dx of integral small u dy minus capital U d delta by dx. So once again, this is for the second term, and let's call this A, let us call this B, and let this left hand side be called 1. So put A and B in 1. And what this will give us is d by dx of integral from 0 to delta u square dy minus u square d delta by dx, and then we have minus, so then the other term was minus u times this du by dx, so minus u times d by dx of integral from 0 to delta small u dy, and this minus and minus becomes plus, so plus u square d delta by dx. So this is the left hand side. And the right hand side of the equation is equal to integral from 0 to delta capital U du by dx dy plus nu du by dy at y is equal to delta and 0. So this will become equal to u du by dx. This is not a function of y. So you can pull it out to the integral times delta plus nu times du by dy at y is equal to delta minus nu times du by dy at y is equal to 0. Now, at y is equal to delta, the boundary layer thickness, du by dy is equal to 0. And the logic for this is that the boundary layer must merge in the outer flow smoothly. And we'll use many more cases like this. And du by dy at y is equal to 0 is not 0. It is the shear stress at the wall divided by mu. Because shear stress is equal to mu du by dy at y is equal to 0. So therefore, tau 0 is equal to shear stress at the wall. So what we'll assume is that either we know or we have to find out shear stress. So we have this left hand side, we have the right hand side, and now you readjust the terms, and what this leads you to is d by dx of capital U square theta plus u du by dx times delta star is equal to tau wall by rho. So let me call this as tau wall. Instead of tau 0, let's call it as tau wall. So this you can check when you look at this left hand side. There are terms like u square minus u square. So this will lead to, and then there is a capital U times small u. So these two will lead to a boundary layer, this thing, theta term, and then you will get this. And so finally you are left with this. What you get is d by dx of u square theta plus u du by dx delta star is equal to tau wall by rho. And this equation which we have, this nothing, this is an exact equation. This is called von Karman momentum integral equation. And this is used to solve approximate solve to to find approximate solutions of the now probably in today's age when we can solve these things on numerically on the computer, it may really not be something so important or it may not be something so keen, but this actually where becomes a was the way how people were moving when we did not have computers. And in this equation, let us just recall theta is the momentum thickness and which is equal to integral from 0 to delta and delta star displacement thickness. This is equal to integral. And tau wall is equal to so this is the momentum integral equation. Okay, so we have derived this. Now what we will do is, before we talk more about the momentum integral equation,